Still catching a few people here and there.
I think you missed me, Professor.
Okay, let me catch you. Okay, anyone else? I'm just looking through the list a little more myself. Another person, okay. Okay, so I think we're good to go here. Okay, can you see the tablet?
Yeah.
Very good. Okay, so let's just start a new, see where we are here. Just go probably to the end. So I think where I'm at here is, yeah, is the problem session that we did yesterday. So if anyone wasn't there, hopefully you can get a copy of it from someone who was. This is problem 19, which is a homework problem, but was also one of the ones on the list of problems you should know. So maybe sometime during the hour, let me know if you need this or if you can't get it from a classmate. For now, I'll just go to another page, add a page, put some lines on it if I can. Huh, doesn't want me to. Let me try again. Oh, that's better. I think. No, I don't think I have the lines on yet. Weird. That's better. Okay, so let's talk about our next meeting, which is, of course, Friday, which is the time of our test. So start off with that important reminder.
Will our test time still stay the same? Because I know you had to talk to the other class about it.
Our next meeting is Friday, March 4th, 2022. And that's the time of our first midterm, exam 1. Our first midterm.
Professor, can I get permission to record?
Sure. Who are you?
Brian?
Okay. I couldn't see your box, couldn't see the box nor recognize your name. So let me see if I can get to you now.
Yeah, me as well, Professor, for Chris.
Okay, sure. Hang on a second. Let me get both of you.
Thank you.
Sure. Chris, I see. You got it. Brian, I see as well. You got it. Is there anyone else, since I'm here, who needs permission to record? Okay. Well, let's just go back. Okay, so that's our first midterm exam. It's going to cover the material that you probably know at this point, which is sections. So it covers sections 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, and 2, 1. Today we'll go into 2, 2, but that will not be on this exam. And I guess it's important that you have this review sheet. I have a copy in front of me. I hope you all have the review sheet. So on the review sheet for math, 4190, it has proofs to know completely. There are 1, 2, 3, 4, 5, 6, 7 proofs to know completely. There are some other proofs to know the meaning of. And there are some sample problems. Is there anyone who doesn't have that review sheet? Good. Okay. So I'm assuming that means you all have it. Great. Now, we did get a little bit further in section 2.1 than we did before, which is the last section. And we got to the point where hopefully you could answer all questions in section 2.1, problems 2, 3, 4, and 5. So those questions, they were lengthy. They first defined a transformation. So it asked you to show that something was a transformation. That we did about a week ago. Then it asked you to describe the null space and the range of the transformation. That we did, after the transformation, a couple of days afterwards. And then more recently, they asked us for a basis of the null space and the range, and also for the dimensions. And that's even more recently. Okay. So there were some other theorems here that I probably should put on the ones to know completely. So if you look at the review sheet, let's sort of look at the review sheet. I would tack on a couple theorems to the last one there. So let me just do that. So in section 2.1, when I did the review sheet about a week ago, we had the last theorem listed there to know was theorem 2.3, and it was to know, not to prove or anything. But after then, we've done a couple other theorems, theorem 2.4 and 2.5. So I would tack that on, look at our review sheet and add theorems 2.4 and 2.5 to the list of know the content of. So add those two to the theorems. It doesn't affect the list about what proofs to know, even though we did prove one of these at least. There, we proved theorem 2.4. So I mean, if you wanted me to add that to the list, because you could ask me to, but at this point, I'm not so eager to add anything to the list of proofs to know. I think we got enough there already. I just want to, I don't want to add these two to the proofs to know, to the list of how to know the proofs, but I do want to add it to the list of theorems you should be aware of, because you need them to answer the questions 2, 3, 4, and 5 in section 2.1. And so we can even talk about that after class today if we need to. There's still questions on how to do that. Okay, other than that, I think the review sheet is pretty much up to date and everything you need to know for the test. Let's talk about the time of the test. So last time we met, I asked if you could start later. And I asked if people could start at 12:30. And I got a lot of good response from this class. Almost everyone could do it except for, I think it was 4 people. I've written their names down. And so I wanted to run that by the other class, and I did, because I wanted it to be a common starting time. And they also, by and large, were okay with it. So for most people, the starting time is 12:30. Not everyone, okay, but just most of you. So for this class, instead of starting at what, 10:45 when we typically do, most of you I will be sending out invitations to at 12:30. So so what does it mean? Don't freak out if you don't get an invitation to class at 10:45, because I've already mentioned this to you. And so you will get an invitation, but later in the day at 12:30. Now let me list the exceptions. There were 4 people who said they could not do this, and that's fine. One was Sean. So the exceptions, and there may be a couple more, we'll see. The exceptions were Sean, I think John Rodriguez. Cynthia, I believe. And Maria. So let me start with those four people. I don't know if they're all here today. I hope so. Juan, you have your hand up, so do you have a question?
Yeah, I also need to get the exemption to start the test early that day. I have worked at 3 that day.
Okay, so you want to also start at the usual time?
Yes, please.
Okay, so the exceptions, and those are the people who are starting at 10:45. And I've just been asked to add Juan to the list. Juan, you're on the list now. Let me make sure.
Thank you.
Let me make sure I've got you on this other list too. Okay, so I have a few lists. But let me make sure of the other people. Let me see if they're here. So that would be the easiest thing to do, I guess. You would think it'd be the easiest thing to do. Okay. Well, I can just go through the list here. Sean, I see. Sean, are you still good for starting at the usual time, 10:45?
Yeah, that would be the most ideal for me.
That's fine. I just wanted to confirm. Let me see who else is here. John Rodriguez, same question. Are you still want to start at 10:45, I assume?
Yes.
Perfect. Thank you. Let me keep going and just confirm with the other two if they're here. Well, I guess I could ask, is Cynthia here? I don't see her on my list of people. Okay, so Cynthia, if you're here, speak up. And the other one was Maria Lopez.
Yeah, I could still start at 10:45.
No, you're still at 10:45. Great. All right, so everyone is confirmed except for Cynthia. And I have one additional person, which is Juan. Is there anyone else who really finds it, who really wants to start at 10:45 rather than 12:30? For whatever reason. Okay, good. So and the rest of you, I assume the rest of you will be starting at 12:30, which is when I'll send out invitations. So I'll send out earlier invitations for these 5 people. And I will send out invitations to start the test at 12:30 for the rest. Now, I guess I have to be a little careful. Yeah, I think it'll work out because all I really have to worry about are the exceptions. So even if some of you are on both mailing lists, so it's possible you get invited twice. And the main thing I don't want to end up confusing anybody is to invite them at different times. But I think I know the 5 people here who are starting early, and the rest of you are starting at 12:30. You have like, 2 hours and 5 minutes at least. But if you could arrange your schedule so you can stay a little longer in case you need it, I probably will give a little more time if it's needed. Okay, are there any other questions about when? There are some people in the other section who needed to start later. So if someone in here wants to start, later than 12:30 for some, schedule conflict reason, let me know. But I don't hear it from anybody. Okay. So,
What is the later time, if you don't mind me asking?
the latest time, well, I have some people starting at 1:30 and even a few at 2:30. And by the way, if you get the invitation at 12:30 and show up at 1:30, that shouldn't be a problem at all.
Do you mind if I send you an email later?
I can barely hear you. There's a lot of background noise. Maybe try me one more time, and if I can't hear it, I'll look in the chat what you're trying to say.
I'll just put it in the chat.
Well, I think you said you just put it in the chat, but I'm not sure that's going to work. We'll see. Let me see if I can get to the chat from here. Let's see if I can even reshare. Stop sharing. Okay, so I think I can get to the chat. Look out for email from me. Is that what you said? Okay, let me see if I can read the email now. I don't.
I'm going to be sending an email out later.
Oh,
I
yes.
haven't sent it yet.
Okay, okay, that should be fine. Just send me it later and it should be okay.
Thank you.
Okay, and is there anyone else? Great. Okay, so that's that, and please make sure you have a computer or laptop that has a working webcam, because I need to be able to see that you're the one taking the test. Okay, so it's that simple. And if you don't have that, you still have a couple of days to arrange that you get a working computer, a laptop, or you could even use your phone. People have done that to let me see you. You could, have a couple hookups that way. But you need to have that in order. And you also have to have abilities to scan or copy your work at the end and email to me. So that's important as well. Please have those things in place so you don't have to scramble and try to make it work at the last minute. Okay, any other questions about the exam? Okay, then let's go back to the math, I guess. Let me see where I am. I just want to reshare. Okay, so today we start, so let me keep an eye on the clock here. I think I'll do some new material for like roughly 20 minutes, maybe 25 minutes. And then I'll do some, close out today's session just by, again, emphasizing some of the things you should know for the test. So make sure I don't speak more than maybe 20, 25 minutes at most on the math here. Okay, so what we're talking about now is the new stuff, new material. Which is in section 2.2. And it brings in, it's on an important connection between transformations, linear transformations, which is what we've been talking about recently, and matrices. Okay, so it turns out, just to summarize, so here's the main result. It turns out that linear transformations can be represented as, so I should make it, since we're here, it turns out that a linear transformation can be represented by a matrix. Okay, and that turns out to be an important connection. In fact, you can recast everything we've done for linear transformations, which is, all the stuff in 2.1, in terms of their matrix representations. So that's what sections 2.2 and 2.3 are about. And just to get rolling, we'll do some examples from 2.2. So the material starts on page 79. And it starts with the concept of an ordered basis. So far we haven't worried about the order in which the basis is coming in, but now we do. So page 79. You'll see this definition. A vector, let V be a finite dimensional vector space. An ordered basis is a basis of V endowed with a specific order. That is, an ordered basis for V is a finite sequence of linear independent vectors in V that generates V. So if you look at that definition, and a good example, let me just look at their example 1. In fact, I'm making their example 1 even easier. They have F3, and I'm just going to replace it by R3 to make it more calculus-like at this point. And if you have a basis, well, why don't we think of the standard basis? The standard basis in R3 would be 1, 0, 0, 0, 1, 0, and 0, 0, 1. That's the usual, unit vector in the x, y, z direction. If you put those vectors together and call it beta, we've called that a basis before. And it's certainly defined, has the definition that I just read out loud. The vectors are what? Linearly independent. And they generate all of, in this case, V, and V is equal to R3. However, we're at this point talking about an ordered basis. So we want this to be the first one in it, the second one in it, and the third one in it. And so if you denote this one is E1, and this one is E2, and this one is E3, this would be the ordered basis, E1, E2, E3, which would be considered different than, say, the basis if you put E2 first and E1 and then E3. So instead of calling this beta now, we call this something else, maybe gamma or something, doesn't matter. But now we're saying that when we list these items, it's a little confusing because when you list the items in a set, you usually don't care about their order, it doesn't matter. But now in terms of this section, we do care about the order, and we want them to come in this particular order where this is the first base vector, this is the second, and this is the third. Okay, well, that's usually how we list them anyway, so it shouldn't be a big deal. But we're now imposing the order that's given here. Okay, that's example 1. If you flip the page, then they give an important definition. So let's look at the next definition. So we're now on page 80. And the definition is this: suppose beta is an ordered basis for a finite dimensional vector space V. So here's the definition we want to get to. Suppose beta now looks like, and we call them U's this time, U1, U2, U3, all the way down to UN. So suppose this is an ordered basis of V, where V is a n-dimensional vector space. Okay. Then what do we know? We know from one of our past theorems, recall, that any vector x can be written as a1 u1 plus a2 u2 all the way to an un, where the a's are unique scalars. Okay, so that's actually a past result. We've seen in the past that if you have a basis of a vector space, then any vector, I guess I should say for x, some vector in here, that x can be written as a linear combination of the base vectors, and that it can be done, that can be done only in a unique way, one way. That's a past result. So far, nothing here is new. What's new is coming. We define the coordinate vector of x relative to beta. We define the coordinate vector of x relative to beta. And they put on this notation. So they have x, they put it in a bracket, and they put a subscript on it of beta. And they're saying, if you just, for x, since these scalars are unique, if you think of it as a column vector, that's what they want to define, where these are a1, a2, ... until an. And they call that the coordinate vector of beta relative of x relative to beta. So that's what's being defined, the underlying portion of this. Okay, so it's new terminology. This is the new terminology, bracket x subscript beta. And what it does is it takes this representation of x in terms of the vectors of beta, and it just represents it as a column vector where these are just scalars. So it sort of de-emphasizes that this is a1 times u1 and a2 times u2. That's sort of understood. And you're just looking at these coordinates, or sometimes called components, and that's called the coordinate vector of x relative to beta. So this, if the scalars here were real, this would turn it into what? This would be an n vector. A vector, you could say, a vector in Rn. So instead of writing a vector relative to the base vectors here, you're sort of converting it to a vector just as a column vector that looks like the Rn. in general, the scalars don't have to be real, so these could be a vector in Fn. But for the most part, we've been keeping the field to be the reals. Okay, so that's the new idea. It's not really a new idea, it's really just more terminology. And then they do a couple examples to drive the point. So let's do a couple examples. So example 2. Need a little more room. Great. Okay, so example 2 of the book says, suppose the vector space is this. Suppose it's the polynomial vector space, second degree polynomials. And do they make it reals? Yes, great. They make it reals with real coefficient. Okay, so what is that? We already know what those are, but it probably doesn't hurt to write. It's ax squared. It's all quadratics that look like this, such that what a and b and c are real numbers. So that's the polynomial, second degree polynomials vector space with real coefficients. Okay, so all right, they want to basically explain this notation when the vector space looks like this. So what they say is, let's take beta to be what we would call the standard base vectors, which are 1, x, and x squared. But in this order now, right? So this is what's called, we've been calling this the standard basis. And now they specifically are listing them in this order where the 1 is the constant here, x is just the first degree term, and x squared is the other. We know from the past that this is a basis. All we're saying is be sure to put it in this order. And if you do that, let's see what they say. So then they say, if you had a function, suppose f of x was a second degree polynomial of this sort, and they give an example. So the example is, suppose it's 4 plus 6x, 4 plus 6x minus 7x squared. So notice they've written it in terms of these base vectors, but they put the constant up front now, unlike what I did over here. And they put this first degree term next, and then this x squared term here, because this is the order they want to talk about. Okay, so what do you know about f of x? F of x is certainly a vector in this space. And if you use their notation, they don't use f of x, they just use f. They put brackets around it and put the beta in here. And what that coordinate vector would be a column vector, where 4 is the first entry, 6 is the second entry, and minus 7 is the last entry. And this is again called the coordinate vector of f, I suppose, relative to beta. That's their example. Any questions about it? Okay. Let's see if I can get maybe one more example done. Yeah, so the last thing is we now proceed with the promised matrix representation of a linear transformation. So let's see if I can get that done and then call it on this material. So suppose you have suppose you have V, let V and W be finite dimensional vector spaces. By the way, most of the way, the rest of the way in the book, we'll be doing mainly finite dimensional vector spaces. And suppose they have ordered bases given by the V's. So with this one, the basis may look like V1, V2, up to Vn. And this one has its own, so this is an ordered basis. Of V. And the ordered basis of W is gamma, which they write this way. And they use W's instead, W1, W2, all the way up to Wn. Well, it doesn't have to be the same dimension, so I should make it M. They're both finite dimensional, but they don't have to have the same dimension. Okay, so you have two vector spaces. This one has dimension n, this one has dimension m. These are ordered bases of both of them. And suppose T is going as usual from V to W. And suppose T is linear. Okay. And here's the main conclusion. Then for each J equal 1, 2, 3, up to N, there exists unique scalars and the scalars are identified as A, I, J, so they're doubly indexed. And the book has it in F. So for now, I'll go with F, but you can think of F as R. And I is going from where? 1, 2, 3, up to M. So there are unique scalars of that type, such that what? Such that the transformation of any of these base vectors of V, so they call it F, Vj, or J could be any of the indices from 1 to N, are represented in this manner as the summation of Aij Wj, where J is running from where? 1 to M. I put that 1, 2 lines to it. That's better. And J could be anything. 1, 2, up to M. Oops, goes 1, goes up to M, sorry. Okay, so to make it a little clearer, let's just write it for each one. I see my time is basically done here. So let J equal 1, for example.
Professor,
Yes,
for the summation, it's I equals 1,
it should be I, you're right.
and then it's WI.
So yes, let's get this right. It's I equaling 1 and it's W I as well. Thank you. Thank you for those. So yes. And I'm about to illustrate what it would look like for J equal 1. So for J equal 1, this summation, I'll write it out longhand. So it would be A11 W1 plus A21 W2 all the way until you get to I being M. So that would be A MJ. Well, wait a minute. Yeah. But J. Let's see, I'm mixing this up. J equals 1. So wherever I have this, I have 1. Better. Times okay, so what it's saying is something that we already know, that if you transform the first vector in the basis beta by t, you're going to end up where? In W. And in W, everything in W can be represented as a linear combination of the gamma base vectors. So these are the gamma base vectors, W1 up to W up to Wm. And there will be coefficients corresponding to V1. And when you're dealing with V1, the second coordinate of this subscript is just 1. And the first coordinate of the subscript runs from 1 to M. So this is how it looks. And I'll probably end with this. Suppose J is 2. Then you're talking about TV2. And I'm writing this, the summation longhand. If you want, you could write this as a summation sign, but I think it's probably easier to see it this way. So in this case, the second index again is J, so it would be A12 W1 plus A22 W2 all the way to get to the last one, which is A, and this is wrong. In this case, let's see if it's right. No, that's right. So it would be AM2 WM. So if you're transforming V2, it again is a linear combination of the vectors in W, which are W1, W2, up to Wm. And the coefficients, the unique coefficients that come with it, are denoted this way, where the sum is happening over the first index, and the second index is indicating which vector you're transforming. Okay, so if you do this for all of them, let's do the last one. The last one would be J. What was J doing? 1 through N, so the last one would be N. J equal N. Then that would be A1 N W1 plus A2 N W2 keep going until you get to the last one, which would be A, M, N, W, M. And if you take all of these coefficients here and here, that's the matrix we're trying to get to. And that we're using that to represent the transformation. So the matrix that we're trying to get to is A11, A12, whoops, I'm reversed, A21. Let me make sure I got it reversed. Well, I think I'll stop here rather than try to clarify it. So let me just ask you to continue to read this section, continue reading, because I want to get back to the exam. So we're on the bottom of page 80. So read this whole section actually. So read 2.2. And here are some problems which will be talked about next week. But to really get a feel for this, I think the problems 2, 3, and 4. Problems 2, 3, and 4 on page 85. And I'm sorry not to go through the matrix a little more carefully here. I think as far as I went is true, but they didn't really represent the matrix in the way I want to yet. So I'll let you pick it up from there. Okay, so this is homework. Let's flip the page. So I'm going back to the review sheet to sort of help us. What happened there? Lost my page. And from the proofs to know, there were 1, 2, 3, 4, 5, 6, 7. At least 3 of those will be on the test. At least 3 out of 7 will be on your exam. At least 3 proofs out of the 7 listed will be on your exam. So I hope you have them memorized or almost memorized, so you don't have to try to memorize them all tonight or tomorrow. There could be, it says at least 3, there could be 4. Okay, so those are things that you know are coming. What else you know is coming? So this is some knowledge of certainty. There will be problems like the homework problems listed on the review. On the review sheet. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9 bullet items there. Each of those bullet items refer to different pages in the different sections that we've covered. And usually there's either 1 or 2 problems or maybe 3 parts of 1 problem listed there. So if you haven't already done so, I would know or look at those kinds of problems, because there will be problems like the homework problems. There will be problems like that on your test. Will they be the exact problems? Probably not, but maybe just I'll change the numbers slightly or the problems slightly. So it would be a good idea, if you haven't already done so, and I hope you have, to work these problems, because those are coming. How many will there be? I'm not sure, but enough, I would say, I'm looking at the 10 bullet items. I'd be surprised if you don't see at least 4 of those kinds of problems on the test. So I'll make that a promise, at least 4 problems like, not identical necessarily, but like those listed on the review sheet. So if you want to have a little peace of mind, go over those problems listed on the review sheet, and hopefully you can do them. And then you probably come in feeling a little more confident. Of course, if we go the other way, you could realize you don't remember how to do them. But I'd rather have you realize that now, 2 days before the test, than on Friday. Okay. What else is fair game? Well, any previously assigned homework is fair game. A couple things came up in the review session the other day. So we did about 4 or 5 problems, including some of the proofs here that you needed to know. And by the way, a problem, which was that? I think it was problem 19 on page 22. I'm not sure. That was a homework problem, but it's very much like a proof anyway. So I listed it under the proofs. When we any previously in this fair game. I lost my thought there. I was going to say something more about it. I guess there's not too much more to say, is that I will be looking at previously assigned homework problems as well, other ones than the ones listed here, and you could expect to see them as well. So I'm trying to tell you how to study. If I were preparing for this test myself, I would know those 7 proofs. Oh, the other thing is you need to know, have to know by heart definitions. Okay. You have to know previous results, even if I'm not asking you to prove them. So I don't want you just to come out saying, well, gee, all I had to know is these 7 things, but he asked me other things. Yes, that's what I'm trying to say about know the content of other things. And I've even amended that content today to include what? Theorem 2.4 and 2.5. So I've listed many of the other theorems that you may have to know, okay? Definitions, there's a bunch in here. Okay, so here's a few. What does it mean to be a vector space? The list is too long to tell you real quick all the things, but you should know. What does it mean to be a subspace? Okay, so those are 2 definitions by themselves. What does it mean to have a set that's linearly independent vectors? What does it mean to span or generate? If you don't know any of these terms, I would write them down right now and go to the index or go to the sections covered and make sure you know the definitions. I mean, if I say, show the following vectors span some space, you can't, if you ask me what does span mean, I'll say, I'm sorry, that's something you got to know. That's a definition you've got to know. There are no notes allowed. So when I say no, I mean no by heart. Before you sit down and take the test, you can't have a list of these hidden or something. This is stuff you need to know. So I'm warning you right now, make sure you know the definitions of these things. What else? T is linear. What does that mean? sometimes there's different characterizations of this stuff, right? I would know a lot of different examples of vector spaces. So the one I brought up today, P2R, for example, second degree polynomials with real coefficients. If I use this symbol, you need to know. If I use this symbol, you need to know. So all of these definitions, and of course, the more common ones would be Rn, things like that. Under things that you probably should know, how do subspaces look? How do subspaces look, say in R2 or R3? So I can tell you, but this doesn't necessarily give you all the information, but at least you should know in R3 and R2, they look like the zero subspace. They look like lines. Let's do an R2. Lines through the origin. And they look like all of R2. That's how subspaces look. We talked about this stuff. Is it in a theorem? Maybe somewhere, but we certainly spent time in class talking about it, and you should know that. So if I give you an example that looks like this, and I say, consider the line that look in R2. So this is the x-axis and this is the y-axis, and consider the line that looks like that, y equals x plus 1, are vectors on that a subspace. You should know from the beginning, no,